go through this example of income and substitution effects when there's a price going down, which is going to make the consumer better off. But when you're talking about income and substitution effects, it involves a solution where we're trying to get that consumer back to the old lower utility level, and then compensating variation is going to be the difference between the original budget level and the new lower budget level. So compensating variation will be negative here. So here we have our utility function, x to the 0.4 times y to the 0.5, Cobb-Douglas, of course. Price of x is 8, price of y is 10, and a $200 budget. So the first problem is always to maximize this person's utility given this information. And our two equations are going to be to set the marginal rate of substitution equal to the ratio of the prices of the two goods. So using our Cobb-Douglas shortcut, the marginal rate of substitution for this utility function is going to be the exponent on the x times y, so 0.4y divided by the exponent on the y times x. We set that equal to the ratio of the price of x over the price of y, and so that's $8 divided by $10. So that's our equation number one. Let's go ahead and simplify that. This is kind of an easy simplification because 8/10 is equal to 0.4 over 0.5, right? So this multiplier on the left we could write as 8/10 y over x equals 8/10, and those two are just going to cancel. When we solve this for y, we're just going to end up with y equals x. We're going to be consuming the same amount of x as y in this problem. Now we want to plug that into a budget line equation like this. Price of x is 8 times x plus the price of y is 10 times how many y we buy has to equal $200. Since y equals x, we can just change either one of these into the other variable. They're going to be the same number. 8x plus 10, replace y with x, equals 200. And we're going to have 18x equals 200. 200 divided by 18 gives us 11.11111 running, and that's also going to be equal to y, since y is equal to x. Since we know that when this person maximizes their utility, given these prices, they're going to buy the same amount of x and y, and it's going to be 11.11. Let's calculate the utility level just by plugging those values into our utility function. So here we're going to have 11.11 to the 0.4 times 11.11 to the 0.5. And we can simplify that because these are the same number, we can add those exponents. We get 11.11 to the 0.9. And on our calculator, I'm getting something about 8.73. So our utility level would be 8.73 in the original situation. However, now this person's going to be happier because the price of y drops from $10 to $5. Now, if you're familiar with Cobb-Douglas utility problems, when the price of one good changes, the quantity of the other good stays the same. So we could use that fact if we wanted to take a shortcut here. Let's not. Let's do the problem, but we'll see that that's true in the end. So now we set up our same two equations. Our marginal rate of substitution again is going to be 0.4y divided by 0.5x. We set that equal to the new ratio of the two prices, which is going to be 8 over 5. $8 divided by $5. If we solve this equation for y, we're going to end up with y equals 2x. So that's our simplified version of equation 1. And then we're going to plug that into the budget line equation, which is 8x plus 5y equals $200. And we plug that in for y right there. And we're going to get 8x plus 5 times 2x, which will be 10x, equals 200, which is going to give us 18x equals 200. See, isn't this looking exactly like what we did before? 18x equals 200? Yes, because as expected, this is a side effect of the Cobb-Douglas utility function. X is going to be equal to 11.11 as usual. But now, since the price of y has decreased, this person's going to buy 2 times that much y. The law of demand is in effect. Y equals 22.222222. Now, when we plug these values in, x to the 0.4 times y to the 0.5, and we figure out how much utility we get, our answer is going to be about 12.35 or so. And it all depends on how many decimal places you carry these repeating decimals out for the x and the y. Somewhere around 12.35, you're good. Now for the decomposition basket. Again, what we're trying to do is say, okay, if this person has a lower price of y and now they're happier, what if I didn't want them to be happier? What if I wanted this person to keep their old utility level? Perhaps we had some bizarre retirement plan, and our retirement plan guaranteed that you were always going to get 8.73 utils in happiness in retirement. We're not going to pay for you to get more happiness here, like this 12.35. So if the prices go down, we are justified in cutting the amount of money we send you for your retirement, just as we would be obligated to send you more money when prices increase. But here, since the prices went down, we're trying to figure out, okay, what could we buy you that is the cheapest thing with the new prices that would get you that old utility level of 8.73? So let's write that down. So our utility level, 8.73. Our two equations are now going to be, equation number 1 is going to be the same kind of thing that we've used before. Second equation is going to guarantee that we get this 8.73 utility level with however much x and y we decide to buy this person. So let's write these down explicitly. Now, since we're talking about the marginal rate of substitution, and that is just 0.4 y over 0.5x, and the new prices after the price change are the ones we're looking at, then really what we're talking about is just exactly the same equation that we had up here, equals 8 over 5. And so instead of doing this all again by hand, we can take a shortcut and we can say this is our simplified version of equation number 1, and we can just bring that down and try to save ourselves a little bit of headache. Now the second equation, instead of being a budget line, since we don't know the budget, it's going to be this utility equals 8.73 has to be equal to the utility function, x to the 0.4 times y to the 0.5. And so we're going to plug in 2x right here for y. And so 8.73 equals x to the 0.4 times 2x to the 0.5. We're going to distribute that 0.5 power, x to the 0.4, 2 to the 0.5, and x to the 0.5. And now we're going to want to collect those two x's by adding the exponents, and we're going to want to divide both sides by the square root of 2, 2 to the 0.5. And so when we do that, let me just make a little notation over here. We're going to divide that by the square root of 2, which is the same as 2 to the 0.5. It'll cancel on the right-hand side. And then when we collect those, we'll end up with x to the 0.9. We're getting close. X to the 0.9 equals whatever 8.73 divided by the square root of 2 is. And I get about 6.17-ish. And again, when I do this, I usually will leave all the decimals in the calculator for further computation. And then in order to get rid of this exponent on both sides, we have to raise both sides to the inverse power, 1 over 0.9. And then we'll end up with x on the left-hand side, and on the right, I'm getting something about 7.5, 7.5. Then we go back to our equation number 1 that tells us that the amount of y we're going to buy is 2 times the number of x's, and so y is going to be 15. And now if we just wanted to double check our answer, we could plug the 7.5 and the 15 back into our utility function to make sure that we're getting 8.73 utils. If we haven't made any mistakes, then this is guaranteed. But what we really want to do now is figure out how much this basket is going to cost. Hypothetically, if we wanted to get this person back to the old utility level, what is the cheapest way we could do it? How much could I cut this person's budget by if they were this hypothetical retiree that was being guaranteed 8.73 utils? So let's plug the numbers we have into a budget equation here, where the prices are going to be the newer prices. So the price of X is going to be $8 as it always was. So let's see, $8 times how many X's? 7.5 plus $5 for each Y times 15 Y's. Add those up, and when I do this, I'm getting an answer of around $135. And again, your rounding might be a little different, and that's okay. So let's graph all of this and then kind of sum it all up, wrap it all up in a bow. So our first solution was 11 X's and 11 Y's. All right, let me just do that in red so it's really easy to see. 11.11 X and 11.11 Y's. We can call that solution A. Let's graph that budget line. So that budget line was $200, price of X 8, price of Y 10. So this budget line is going to mean if we spent all of our money on X's, we could afford 25. If we spent all our money on Y's, we could afford about 20. And if we connect those with a straight line, we should have a line that goes through that point A. All right. Now, our second budget line, the same budget, $200, but now the price of Y decreased to $5. So let me do this in purple. We can still afford the same amount of good X. We should always label our axes here. But now we can afford more Y. $200 divided by 5 means we could afford 40 Y's. So here's our second budget line after the price change. So our opportunity set, the things that we can afford to buy, has increased, and we're going to be able to increase our utility. And our solution there was still 11.11 x's, and if we just go straight up here, we should end up at about 22.2 y's, and that's pretty close. So that's solution B. Now let's double check the utility levels here. In problem A, we said that we could get between 8 and 9 utils, and this purple indifference curve right here is the one for 8. And then this golden one is the one for 10. And so we are indeed in between 8 and 10, and so that kind of checks out. A little closer to 8 than 10. Makes sense. And in the next problem, we said we could get a little over 12 utils. And this green indifference curve right here is for 12. And our optimal point B is a little bit beyond that indifference curve. So that checks out. And also, if we just pay attention to the slopes here, again, what we should be seeing is that if we drew a tangent line to these indifference curves that are nearby our solution, that they should have about the same slope as our budget lines. Similarly up here, if we drew a tangent line to this green indifference curve, it does look like it has about the same slope in the area around that solution. So things are looking pretty good. Now our final solution, our budget is $135, and to draw this budget line, we're going to take the price of X and the price of Y and divide 135 by those prices. And so up here, we're going to have 135, let me choose blue here, 135 divided by $5. So if we spent all of our money on Y, we could buy about 27, okay. And then 135 divided by 8 is 16.875. So somewhere in this neighborhood, a little bit less than, say, 17 there. 16.875. Connect those with a straight line. And what we're looking here for with this straight line is, number one, that this blue line needs to be parallel to the purple. Check. Number two, our solution here of 7.5 x's and 15 y's has to be on that line. So 7.5 x, 15 y's. So there's 7.5 x's. If we go up to our budget line, then that should be 15 y's. And indeed, it looks good. We'll label that point C. And also, C and B need to be parallel, these two budget lines, but then C and A will cross. And what C and A are doing is, if we were to sketch in an indifference curve, let me do that. Let me sketch in an indifference curve here for that 8.7. 8.7 utils. I'm just freehanding this, and it needs to be tangent to the budget line for C, tangent to the budget line for A, and basically follow the same general shape as the other indifference curves. But it needs to be in between the indifference curve we have for 8 and 10. I didn't do a bad job there, actually. That's pretty good job for me anyway. So utility equals 8.73. I'll put a little squiggly equals there, since we know that's just me doing it by hand. But it kind of helps us visualize what's going on here. When we move between C and A, we're rotating around that indifference curve for 8.73. Two different ways to give the person the same utility, but there are two ways to do it that are the cheapest given two different sets of prices. So between A and C, the price changed. Between C and B, the income changed. An income shift is a parallel shift. Price change is going to be a rotation of a budget line with a different slope. Okay, so let's sum everything up here. So let's draw my little graphical line that I like to do. And so in this case, what's the lower amount of the good Y? So when we're talking about income and substitution effects, good Y is the one that we're going to talk about because it's the one whose price changed. So the price of Y went from 10 to 5. That's what's driving our discussion here. So good Y, we were buying 11. So 11.11, so this is for Y. And after the price change, price dropped, we bought twice as much. And then this hypothetical basket said we should buy 15 if we were to compensate the person for the price change, which in this case means taking money away. Now when you're drawing these little demonstration breakdowns for income and substitution effects, you want to make sure you put the decomposition basket answer sort of in the right place. And so is 15 going to be closer to 11 or closer to 22? Looks like it's going to be a little closer to 11, so let me put it a little bit more on the left side here. 15. So here's our original point, final point, and the decomposition basket will always be in between those two. And then we want to label between which two is the income and which two is the substitution. And you always know the difference between the two parallel lines is the income effect. So B and C is the income effect. And therefore between A and C, that rotation with the different slopes shows you the substitution effect. And we want to calculate that. We know the total difference here is 11.11, right? And we want to break that into two parts. 15 minus 11.11. That part there is going to be 3.89 of the total change of 11.11 is the substitution effect. That's the amount of the increase in this case, the amount of the increase in the purchases of Y that is explained by the fact that the price changed. The relative opportunity cost of these two goods has changed. The rest of it, 22.22 minus 15, well, that's going to be about 7.22. That's going to be the income effect here. So a larger portion of this consumer's behavior can be explained by the fact that they felt richer after the price went down. They felt like their income was being stretched further because they could get more bang for their buck. They could get more out of their money. And the compensating variation, again, that's how much money we could take away from this person. And the formula for that is how much income after. So we'll say the income that is represented by the decomposition basket minus the actual income. And so here we'd have $135 minus $200, or $65 less. So if we wanted to change this person's income to make them just as well off as they were before the price change, we'd compensate them by taking $65 away to make sure that their utility had not changed. Kind of a little bit of a strange idea in this case. So the price of Y went down. In response, this consumer bought more. They bought 11.11 more. They bought 3.89 more to reflect the different opportunity costs because the ratio of the prices changed. They bought 7.22 more because of a wealth effect or an income effect. They felt richer because prices went down and their real income went up. So this is Dr. Berkey signing off. As always, if you have questions, please let me know. Otherwise, wish you the best of luck, and I'll talk to you later. Bye-bye.